Today's video is on graphing distance and time. We've already talked about how distance and time are fundamental variables in physics. So in this video, the essential question that we're trying to answer is how can we use graphs to understand the relationship between distance, time, and velocity. We're going to start with the process of setting up a graph. So let's say you and a classmate went outside and you collected data on that classmate's position as they moved around over the course of a few minutes. If time is being graphed, time is always the independent variable. And this is because you can't control it. Time is always moving forward. And because it's the independent variable, we're going to put it on the x-axis. In this case, distance will be the dependent variable because the distance or position of your classmate, it depends on the time. And since it's the dependent variable, it goes on the y-axis. One important thing to note here is that you don't just want to write time and distance, you also want to include the units for time and distance on the axes. So for time, that would be seconds, and for distance, it would be meters. Next, we're going to decide on a range to make our graph, a range and a scale. So you want a range that is just a little bit larger than your data set so that your data is going to fill the whole graph page. You don't want the range so big that all your data ends up getting plotted squished in a corner somewhere. So next you will plot your data points. You can do this with circles or X's, whatever you decide. And then you're going to want to put the simplest best fit line or curve to your data that matches your data. So remember, we're not connecting up all these little points with straight lines. We're looking at the overall trend in our data. Looking at this data, one simple line is probably not going to work for us. So instead, we're going to have multiple best fit lines since we seem to have three distinct intervals on our graph. So the three intervals I see here are from like 0 to 25, 25 to maybe around 62, and then from 62 up to approximately 100. So we have three distinct sections on our graph, and with a best fit line to match each of those sections. So now we've got our graph set up, and we want to ask ourselves what it is we want to learn from this graph. We have three different chunks that have best fit lines matched with them. And the first thing I notice about this graph is that the direction of the best fit line changes. So sometimes it's slanting down, sometimes it's flat, and sometimes it's slanting upward. So what does this tell us about the motion of that object? There are a few other things. There's like the steepness of each best fit line, whether it's steep or shallow can tell us about the motion of an object. The length of the best fit line tells us something about its position over time. And also we can look at the x and y intercepts. So each of these things helps to paint a better picture of what exactly is going on with the motion of this object over time. So we're going to look at a new graph now that has best fit lines that represent a purple car, a blue car, and a green car. You can see that the purple car has a slope of the best fit line that's in an upslope direction. The blue line or blue car's line is going in a downslope direction, and the line representing the green car is flat. So what does the direction of the slope tell us about the motion of the car? So you might want to pause the video just for a second so you can think about that. So the slope of the line can tell us whether a car is moving forward, backward, or if the object is stopped. The purple car in this case is going from a distance of 0 kilometers to a distance of 3 kilometers if you follow that line. And we're saying that that's moving in the forward direction. It's going positive. Its distance is changing positively. In contrast, the blue car, which goes from a distance of 4 kilometers to a distance of -8 kilometers, is headed in the opposite direction. So sometimes we say it's going backwards in contrast to the purple car, but the truth is it could be pointed in that direction. It's just moving in the opposite direction. The green car is consistently sitting right at a distance of 3 kilometers as time goes on, so that means that this car is stopped. Its position is not changing. The next graph characteristic we're going to look at to help us understand what's going on is slope of the best fit line. So in this graph, we want to figure out what the steepness of the slope tells us about the motion of the car. So we have 3 cars. They're all headed in the same direction this time. The blue car is starting at 4 kilometers distance and is moving all the way to around -8 kilometers distance over 6 seconds, which gives us that steep slope to the blue line. And this contrasts with the line that represents the green car. The green car starts at -7 kilometers and only moves to about -8.5 kilometers. So when we're looking at the 2 different cars, which one is traveling at the faster speed? In this case, the blue car is traveling at a much faster speed than the green car. We know this because it covers a lot more distance in the same amount of time. So the slope of the line can tell us whether an object is traveling either fast, medium, or slow. The next characteristic we're looking at on a graph is the length or duration of the best fit line. So the length of that line is essentially just telling us how large or small the time interval is over which we're evaluating the motion of an object. So in this case, the purple car is moving forward for 6 minutes. The blue car is moving in the opposite direction, backwards, for 4 minutes, so and at a higher speed because it's a steeper slope. And the green car is only staying still for 2 minutes. The last part of this graph that we're going to be looking at is the intercept. So what do the y and x intercepts tell us about the motion of the car? So at some point we have decided what 0 distance is, and that can be, we call it the origin. The purple car is moving forward or away from the origin in a positive direction. The blue car is a little bit different. The blue car is starting already at 4 kilometers away from our origin and moving back towards the origin. So the blue car is moving from 4 kilometers away towards 0. So if our origin that we designate is our house, so the distance at 0 is started at our house, the purple car is moving away from our house, the blue car is starting somewhere away from our house, moving towards the house, and then keeping on going past the house. So in this case, the y-axis is telling us, or the y-intercept is telling us where we are starting from. And once our lines cross the x-axis, we're passing through the origin, or what we're calling our 0 point. So in summary, when you're trying to figure out the relationship between 2 different variables, we use graphs as a tool. And make sure that you're looking at your best fit lines that you've drawn on your graphs, not the actual data points. We can learn a lot from looking at the direction, slope, size, and intercept of each of these lines. And here's a challenge question. What would a graph of an object going backwards and slowing down look like on a distance versus time graph?